Dear world, welcome back to the new session of string algorithms. So previously we have studied the prefix trie, compressed prefix trie, then we have studied the ternary search trie, and in today we are in the suffix tree. We are basically in the suffix tree. So before we understand that what we will be studying in today's video, let's understand the content in the left section. Look, today we are going to study the suffix tree. So first we will be understanding the concept of suffix tree. That what is suffix tree, why is suffix tree. First we will understand the concept of suffix tree. Then properties of suffix tree. Suffix tree has some important properties. Why do we actually require the suffix tree over those prefix trie, compressed prefix trie or TSTs, etc. Why do we require the suffix tree? We will know that reason. Second, the key characteristics of, it's not TSTs, it's suffix tree, typing mistake. Now the general insert, search and delete operation on suffix tree. Now look, there is a word general. So first we will be observing the general method. That means the general brute force method, which will take the time complexity of big of n square. That will take the time complexity of big of n square. So first we will be observing that number one method. Second come, we'll be observing Ukkonen's algorithm. Ukkonen's algorithm. So there is one important method in suffix trie, that is Ukkonen's algorithm. So in second we'll be observing the Ukkonen's algorithm. Then after we'll be observing again the method of insert, search, delete, etc. operations, but now using the Ukkonen's algorithm. And do you know what is the benefit of this Ukkonen's algorithm? That it entirely optimizes the time complexity from big of n square. From big of n square, it reduces the time complexity to big of n. And this is the benefit of Ukkonen's algorithm. That means if we study the suffix tree, we must use the Ukkonen's algorithm. And believe me, the Ukkonen's algorithm is really tough, but we will understand in very easy manner. So look at the diagram that I have provided in here. First observe this representation, normal suffix trie. So can you observe this one? This is the representation of normal suffix trie. First observe what we have done in normal suffix trie, that we have first utilized a root. This is the root section. That is the root section, and from this root section we have started inserting the word. And in normal suffix trie, we insert all the suffixes one by one. So there are many people who might be thinking what is the suffix is. You might be confused regarding what is the definition of suffix. So okay, let me tell you the definition of suffix. Let's say we take a word banana. BANANA. So suffix is something that it always starts from anywhere in between. Suffix can start from here, it can start from here, or it can start from here also. But the main important things about suffix is it will always reach up to the end. That means if it starts from here, it will come up to the end. If it starts from here, it will again come up to the end. So the suffixes of this word can be banana. Why? Because we started from the starting. We started from here and we came up to the end, banana. We started from A. Let's say we started from A and we'll again come up to the end, anana. Na. Again, if we start from A, we'll come up to the this here. So that will be AN. That will be ANA. So if you start from N, if you start from this word N, and if you again come up to the end, NANA, NANA, NAA. So these all are suffixes. These are suffixes of the word banana. Suffixes. These all are the things, suffixes of the word banana. So suppose if you think that if you just take a word from here to there, from this section, ANAN, this is not a suffix. Why? Because the suffix must approach or must be up to the end. It must be, but here we didn't include the end. The end is A and we didn't include the A here. So this is not a suffix. So to be suffix, we must be up to the end. There should be the letter ANANA, and this is the suffix. So you got idea about what is suffix. Now let's move to have an idea about this concept. So now first look, the largest suffix. The largest suffix here was what? Banana, then anana, then nana. Then the largest suffix here was ana, na, and we inserted all the suffixes here. B-A-N-A-N-A, this is banana, this is anana, this is nana, this is ana, this is na, and this is a. So we inserted all the suffixes, all the possible suffixes of a word we inserted. And now look, one important thing here, that there is a special character dollar. There is a special character dollar. There is a special character dollar, 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 dollar. Not only here, this special character is in all types of suffix trie. That means if you are in the suffix trie, normal suffix trie, general, or in the compressed suffix trie of Ukkonen's algorithm, there is also dollar. So you might be thinking, what is dollar? Listen, this dollar represents the end of a suffix. This dollar represents, dollar always represents end of a suffix, end of a suffix. This dollar represents the end of a suffix. If there is dollar, that means this is the end of a suffix. In terms of programming language, if you just pass here dollar, that means that is the end of banana suffix. This is also a end of suffix, end. And suppose there is not this dollar, so this is not the end. That means that this can be a part of another word like am, or or whatever an. So that is not an. To mark it as an, we have to make it a and the dollar sign. This is very important in suffix algorithm, the dollar sign. So that is suffix, and that was the general suffix tree. Now we came back to the compressed suffix tree. Look, this is the compressed suffix tree representation, and this compressed suffix tree is utilizing the Ukkonen's algorithm. What is the most important suffix algorithm here? So first, what we do in the suffix tree, what we do in the Ukkonen's algorithm, that we compress the most possible, most common suffixes. If suppose three suffixes are sharing the same prefix, then we compress them into one, and that is the function of Ukkonen's algorithm. So first we have this banana, then this is ana, and they have gone through this and they have formed this anana, and now we can see it in the tree structure. This is a dollar, that means this is the ending of a suffix. From the end side, if you observe this a, so they have marked it as the a, so that is the end of a suffix. Then bana, this is another suffix, then this is another suffix na. So there are a lot of suffixes from this, and they have shared the common prefixes in between region. These are the common prefixes that has been shared by the suffixes, and this is the importance of Ukkonen's algorithm. So come in the next part, suffix trie, and we observe that suffix tree is of two types, the major two types. One is compressed suffix trie and one is uncompressed suffix trie. So uncompressed suffix trie, first we will be studying the uncompressed suffix trie. Uncompressed suffix trie, uncompressed. First we will be studying the uncompressed suffix trie. We also call this uncompressed suffix trie as general suffix trie, cause the first concept that came, that was this general concept, general suffix trie. And the time complexity that occurs in general suffix trie, that goes up to big of n square. That means it takes a very huge time. That means it is not an efficient method. Not efficient. So we are marking as not efficient, because big of n square, this is never efficient. We always try to reduce in linear time complexity. So the linear time we try to reduce. Our course main focus is to reduce this into big of n linear time, and this is always our mission. That is the main mission. While we practice algorithms, we try to practice the questions numerical in lead code or code forces. That is our main motto, to reduce the time complexity to linear or more or less. And this is observed using Ukkonen's algorithm. This can be obtained using Ukkonen's algorithm. And this Ukkonen's algorithm is called compressed suffix trie. So this is done utilizing the Ukkonen's algorithm. Okay, now let's study the concept from here. Suffix tree. So a suffix tree is a compressed trie data structure. Compressed trie data structure used to represent all the suffixes of a given string. As I told that suffix trie is a compressed trie data structure that is used to represent all the suffixes of a given string. Look, the given string banana, and in the suffix trie we represent all. This is all. We represented all the suffixes, all the suffixes. So that is told that we represent all the suffixes through suffix tree. It's particularly useful in problem involving strings. So we mainly use the suffix tree in measure a lot of problems. In problems involving string matching, substring searching, and longest repeated substring. Not only these, that has a lot of major applications to solve problems, and we will observe all those applications and type where we can apply the suffix tree. Key concept of the suffix tree. Look, in suffix tree, while we solve the suffix tree using Ukkonen's algorithm, we get something calling nodes. Then we get calling edges. So each node represents a point where the string branches off. So where the string branches actually divert among them, that is called node, and I think you know it. And edges between nodes represent substring of the original string. Suffix, every leaf node represents a suffix of this string. Look, every leaf node represents, whenever we get a leaf part of any node that represent a suffix of this string. And here I have also mentioned the compressed trie linear time. So all the things that is written here I have told you. So we can just escape. Suffix tree is compressed. So there is same things of suffix tree application, and these are pattern matching, longest repeated pattern matching. So this is suffix tree. There is something called one more thing, that is suffix array. So let's understand what the suffix array is. Suffix array. A suffix array is a sorted array of all the suffixes of a given string. It's closely related to the suffix tree, but instead of a tree structure, it uses an array. Look, in suffix array we actually use an array, making it more space efficient. So actually suffix array is that type of data structure, where we actually in the array format we store one by one all the suffixes, and it is a memory efficient, and that's why we utilize the suffix array. The suffix array stores the starting indices of the suffixes in lexicographical order. Here the indices are stored in lexicographical order, so you can call it this lexicographical order as alphabetical order. Type of alphabetical order, what is followed in dictionary. Alphabetical order that is followed in dictionary. Now sometimes a rank array is maintained to store the rank of position, and naive approach takes big of n square log n, but advanced algorithm like using the longest common, it takes n log n. So these are the application of suffix tree. Now we'll come to the main things of all those. So this is what I have already saw you, the suffixes. Observe it. Suffix tree, this is suffix banana, and these are all the suffixes. These are all the suffixes banana, anana, na, and this is the suffix tree structure from how these are represented, and that is suffix array. In suffix array these are all the suffixes, and in lexicographical order, that is dictionary wise, they are arranged in dictionary order and have been provided a corresponding indices in the original string. So that is not main part. Main things that we'll be discussing, the compressed and uncompressed trie. Compressed and uncompressed trie. So before we move to the compressed and uncompressed trie, before we understand one by one the compressed and uncompressed trie, we should understand the code part. So we came to this is suffix tree. So let's see the applications of suffix tree. Here I have told you the major applications of suffix tree. So types of problems solved by a suffix tree. Observe, first we use a suffix tree or suffix tree can be used to solve various string related problems. Look, using the suffix tree we can solve string related problems. String related problems can be solved using the suffix tree. So what type of string related problems? Substring search. Suppose you want to search substring search, that is named as substring search. So for finding the substring from the main string, we can utilize this substring search. Problem, find if a substring exists in a given string. Suppose if we get a problem like this, banana, and if we want to check something like nana, if it exists within this here or not, if you get that type of problem, then we can apply this suffix substring search, we can apply this suffix trie. Second, searching for a substring in a suffix tree takes big of m time, where m is the length of the substring. And look, this is very optimized algorithm, that's why it takes only very less time. It takes a time around only big of m. To search this substring only takes big of m. And what this m represent the length of substring. Length of substring. It represent the length of substring. Length of substring. Okay, next, pattern matching. Second, what's written here for pattern matching? For finding pattern, we can use this. Problem, find the number of occurrence of a pattern in a text. Suppose the text is, again, let's say the text to be banana. Let's say the text is banana, banana. The text is banana, and suppose we want to find the number of occurrences of a pattern, that is number of pattern. If you get problems like to find the number of patterns, so for finding the number of patterns, we can utilize this. And using this algorithm, it again takes a time of big of m. It also takes a time of big of m. Third, longest repeated substring. If we get problem like finding the longest repeated substring, find the longest repeated substring that appears more than once in that, then also we can use this suffix. For this problem also we can use this suffix. For finding longest repeated substring, suffix can be utilized. So these are three. Now we'll be observing more applications. Now look, there is written longest common substring between two strings. To find the longest common substring, let's say mango. So this is a string, and let's say manners. So this is a string, and now look, they have a common strings. Now the word mango, man, and the word man. So these are the common. To find the longest common string, to find the longest matching common, this suffix trie can be used. We can utilize the suffix trie there. So this is for finding the longest common substring between two strings. And it actually takes a time complexity of big of n plus 1. It takes a time complexity of big of n1 plus n2. So n1, this represents the length of first string, and n2 represents the length of the second string. Palindromic string. Problem, identify all palindromic substring in a string. Suppose there is a large long string and there is palindromic string. So the term palindromic string, substring, many of you might find that what is this palindromic. So palindromic is a string. If you write generally, if you write the string and if you write the string in reverse order, they will be same. Like let's say apple, not apple, let's say A P P L P P A. So this is, if we write it from this side or this side, from whichever we write this word, we will get the same things. If you write this here A P P L P P A, so this is both from forward and backward, the word is same. This type of strings are called palindromic strings. These are called palindromic strings. So to find identify all the palindromic strings, we can use this. So for palindromic substring searching, this suffix trie can be used. Longest prefix matching. So to find any longest prefix matching, we can again utilize the suffix array. Find the longest prefix of one string that matches the beginning of another string, and this also takes a time complexity of big O of m. So these are all the use cases, applications where we can use the suffix trie. Now after we have understood the suffix trie, there are two main ways we can implement the suffix trie in code section. First, that is general, that takes big of n square, very huge time, but the code is very easy. And second, the Ukkonen's algorithm, the code is very difficult to understand for the first time, but it takes very less and very efficient time complexity big of n. So we'll be understanding that. So there are more. For finding lexicographical substring, we can again use the suffix trie. And for suffix array construction, for constructing the suffix array, we can utilize the suffix tree. Now time and space complexity, I'm telling you again and again, so we'll come into this time and space complexity later. I think you have all got to understand. Normal suffix tree, no compression. Now let's look how we normal suffix trie. First we have taken an example of banana. Let's again take that example. Let's say we have a word banana, B-A-N-A-N-A. So to insert that word, what we does, first we initialize a root. To insert this word, first we have to initialize a root. So for that we'll be initializing a root. Let's say we initialize a root here. This is root. That is the root section. And from here we insert all the suffixes. I mean, how many number of possible suffixes are, we insert all suffixes that I observed you, and it starts from the beginning. So first we insert the largest suffix starting from here, and it's up to the end. So we insert banana, B-A-N-A-N-A, and we mark dollar. That is, this is the end of the word. That means that is the end of the word banana. Second, we add in second step, that is the first step. In second step when the word is done, b insertion is done, again from the root, we insert B-A-N-A-N-A dollar. Now insert from here, we insert this section, A-N-A-N-A, A-N-A-A-N-A. So this is, we actually insert the entire node. Now after A is done, we will start from here and up to the end. So we will insert N-A-N-A. So once this is done, in the third stanza, banana, the word is banana. Look, the word was banana, B-A-N-A-N-A. So we have already inserted B, we have inserted A, we have inserted N. Now we'll be inserting A. So we will again start from the root. We will start from the root position. This is the root, and we will insert all the suffixes. So B-A-N-A-N-A dollar, the end of the word. Second, A-N-A-N-A, and we are marking dollar as the end. N-A-N-A, and again dollar as the end. Now A-N-A-N, now dollar as the end. So now we have inserted this A also. Now we will start from N and we'll move up to the end, N and A. Again we'll be marking as the end. Now after N is inserted, now we'll be inserting this A. And now we have inserted A, and this is. And this is how we insert all the words one by one. We insert all the suffixes and it forms. This entirely forms a normal suffix tree. As we insert all this is much memory inefficient. First problem what we face here, that it is memory inefficient. That means it takes a lot of memory. It takes a huge amount of memory. So memory inefficient. First, this is memory inefficient. Second is that it also takes a huge time, because we use the brute force approach, so it takes a lot of time, and the time becomes big of n square. So this is the problem of normal suffix trie, because we don't apply compression here. Both the time and space complexity is very much greater. So actually we are in the code section. So we could write the code also in VS Code, and okay. So we are actually in the code section, that you can see class suffix trie. Here I have declared the suffix node. This is the basic tree. So as you can observing this portion, that portion is actually where we are defining the suffix tree node. So I've given you all the hints that, okay. So the things that you saw, first what we have done here is observe. If we just zoom this, first we have created a suffix tree node. When first we was there is the root. We got a root, then from root we inserted the first suffix bana. So here we are actually working in the same manner. So before we do that, we actually this insertion b, this insertion a, then again a. So these are actually this portion, these are one node, and this node is nothing but the suffix tree node that we actually declare suffix tree node. That things is nothing but this suffix tree node that we have declared here. So observe it here. First we have declared the class suffix tree node, then we have declared static final integer maximum character 256. Here maximum character is 256 because the maximum value of ASCII, the maximum ASCII value possible is 256. That's why this is 256. Now suffix tree node children equals to new suffix tree node maximum character. This is here to store, to hold references to child node. Actually in this children will be storing references. Here there can be a lot of references of this suffix tree node type, of this type. So we have constructed a children. Now there is integer start in to mark start and end to mark the portion of the string input representation. And now we have used our suffix link. Here we have also used a suffix link variable. This is suffix trie, and we have initialized it using the suffix tree constructor. After creating the node, now we inserting process. For that we have created a class suffix basic trie, and after using the suffix basic trie we have started the entire main code. So first we have declared private final string text. This is the text through where the value gets initialized and we try to insert it. Then now private suffix tree node, we have created the root from where we actually started. So this is the root. We initialize the root here, root node of the tree. Now again this is the constructor, and through this constructor we initialize the object of this class. So this dot text, the text got assigned here, root new suffix tree node -1 comma -1. This is the start and end index, and build suffix tree. We are using another function build suffix tree to create the entire suffix tree. Now for this particular word, the suffix tree start getting constructed. First in n we actually take the length, whatever the length, and for that we apply the function add suffix of I, and all the characters gets added. Now so we come to the function build add suffix, and here actually we apply all those, and this is where we have actually added. So I think we should keep it in the concept wise. We'll understand the algorithm, the coding section in the next video. So after this, that was the general tree, and that took the time complexity for this code was big of n square, and that is why it was inefficient algorithm. Now we come to the Ukkonen suffix tree compressed. Key concept of Ukkonen suffix tree: implicit suffix tree. We actually declare implicit suffix tree in Ukkonen suffix tree. Instead of inserting all suffixes at once, which takes big of n square, what we used to do, we used to insert all the suffixes at once in normal general suffix tree. But in Ukkonen's we incrementally add one character at a time. That means here we don't insert ba, na, na, the entire suffix that we used to add in one way. Now we add one character. We add first b, then we add a, then we add a, and then we add a. That means here we add one by one character in Ukkonen suffix tree. At every step the tree remains implicit, meaning some parts of the tree may not be fully expanded into node, but this helps in building the tree in efficient big of n. Here we actually insert one by one, so it actually efficiently takes big of n time, and here all the nodes are not expanded always, fully expanded node. Here all nodes are not expanded. Now here is one important thing, is suffix links, which plays a major role in suffix tree, that is suffix links. Suffix links. So suffix links. Suffix links allow you to quickly jump between different parts of the tree during construction. Suppose there is our tree, that is the root, and we have inserted A, then we have inserted B, then we have inserted C, then we have inserted some. So suppose we want to jump from here to here. So this is directly possible, jumping from here to there with the help of suffix links. If there is not suffix link, then we would come to root node, then we would apply recursion, we would check, and then we would storage. But using suffix links, it becomes very easy. That is stored here. Suffix links allow you to quickly jump between different parts of the tree during construction. When a suffix is partially constructed, suffix links help us to continue building the next suffix without restarting from the root. Look, without restarting from the root, suffix links help us to continue on the next tree. This drastically reduces the amount of redundant work optimizing the travel process. And this is the thing that optimizes the traversal process. So there are some three active points. In Ukkonen's algorithm, we get to know about three major active points. And these three active points plays a crucial role. This actually plays a crucial role okay. So there are three active points, and these are active node, active age, and active length. So these are the three active points that I was talking about. Three major active points. So active point, it keeps track of where the next insertion starts, and these three most active points in Ukkonen's algorithm. These three are first, that is active node. Second, that is active age, and third, that is active length. So now look, active node, current node where the extension starts. So from where actually we start extending or inserting the character, that is the active node. Second, active age, the age character currently being extended. So when we are extending any age character, that is called the active age. We maintain that active age also here. This is active age. And the active length, how deep we are into the age from active node. So in how much depth we actually move from here. So how much depth we move, that is active length. This is called the active length. Suffix links, as I told you, they help us to optimize the tree. We have already talked about the suffix links. So now we will be observing the step-by-step explanation of Ukkonen's algorithm, that how we construct the Ukkonen's algorithm. So first we will be observing for inserting the Ukkonen's algorithm. So actually we start from the root node. Here that's told, but I am telling you. So suppose we insert the banana using Ukkonen's algorithm. Banana, B-A-N-A-N-A. So first we actually add B from the root. From root, we have a root here. Let's call it root. And now we first insert the first character B. First we insert the first character B, and we create a new edge from the root to leaf node, and this is our new edge. This is the new edge we created from root to leaf, new edge, and that is root, and this is right now this B is our leaf, that is the leaf. And now we also add a $sign to indicate the end of the suffix. Now we add here a $sign to indicate the end of the suffix. Now after we have added this B, now we add A. We add the second suffix A. After we have added this A, so from B we have created a new edge for A, and we again end this $. This marks the end of this. So now our tree represents two suffixes. This B is the suffix, this A is the suffix. After this we insert the next character N. From here we insert the next character N, and again it marks the end. So the tree represents three suffixes right now. So after we have worked with this character, now look A. This A is already available in here. So instead of creating a new, we will just come to here in this section, and after that there is N. So we will be inserting this N. We will be inserting that N. So from here we insert this N, and the $ becomes after 8. So this is. So after that we have inserted AN. So after this character, when we are in the N, that is we get the letter A. So when we are in here N, instead of creating a for n. From here we add the next suffix, we add the a, and this is dollar. So this is how the word is insertion is done in the Ukkonen suffix tree. So actually the insertion is quite complex. It was difficult for me to also understand. If you get more better source from it, also provide me the link in the comment so that I can understand. So this was all about the active, and as I told that to maintain the entire node, here three things majorly applied are active node, active age, and active length. We very much use here the concept active node, active age, and active length. These are very much used in here. So we'll be observing towards the coding section. We will not actually understand, but we will have a look of the coding section. So this is first we create the suffix tree node. First I have created the suffix tree node here. As you can observe, this is class suffix tree node hash map. So I have created a hash map for this. Then we have marked integer start in. Then this is suffix tree node suffix link, the very important link which actually helps us to jump from one to another. I mean, we need to jump from one character to another character, let's say. So this is done by using the suffix link, where this is the constructor we have initialized. Now we actually start working in the suffix tree. So as you can see, the suffix tree, private string text, private suffix tree node, private integer current name. So this is suffix tree. After inserting the suffix tree, I have started inserting private void extend suffix tree. Using this extend suffix tree method, I have started the insertion of characters one by one. So after that, extend suffix tree, that method keeps on running, and this method is really very used. So we'll be observing this in another section. And if you want to see the codes to be compiled, so let's move towards the code. So first we'll be observing this is suffix tree basic. Let's apply CLS, and now observe this file is between this suffix tree. So we'll be changing directory command suffix tree, command suffix tree. And now we want to run this file java suffix tree basic.java. Sorry, first we have to compile the file java compile -d dot, and now we can run this file suffix tree basic, and you can see we got the outputs based on that. First we try to insert this word banana, and now we are searching the prefixes ana, ban. So these are actually correct suffixes, so we got true, and this abc not possible suffix, so we got the false here. And you can see first here we have declared the suffix tree node. We have declared maximum character, suffix tree children, integer start in, what marks the end, and then the constructor suffix tree basics. Here we have initialized using the constructor, and here again using this function all characters has been added towards this. So we'll be looking the entire coding section in next video. And this is the optimized method using the Ukkonen's algorithm. So this is creation of suffix tree first, and this is hash map, and with respect to hash map we have mapped with respect to character and suffix tree node. This suffix tree node will actually store the suffix links. So this is still a new hash map, integer start in, and here again we have declared a suffix tree node suffix link. Now we have initialized here, and this is the entire long code of Ukkonen's algorithm. First suffix tree, then this is string text, root, current, end, last created internal node. Then these are the active points that are very important in our code, that is private suffix tree node, active node, private integer active age, private integer active length. So after creating all the length etc variables, we have initialized through the constructor this dot text equals to text, this dot root equals to new suffix tree node -1 this dot active node equals to root. We have initialized the first active node as the root. Then this dot active age equals to -1, that means there is no age. This dot active equals to 0, that means not initialized. -1, this dot current end equals to -1, keeps track of the current page. And then this dot last created internal node equals to no internal initially. Then we have called the build suffix tree function from here, So then it will start actually building the suffix tree from that portion, and this is the method. So we are traversing one by one all the character, and we are inserting through the extend suffix tree. So the method changes from there, from here, that it has entirely another type of code, and this is large code. So I'll be making video on how we can make the code and we can write this entire code. Here we can see we have splitted based on, so we'll be observing the entire code and search operation in the next section. So I'm ending this video here. So let's look what we have understood in this video. Let's have a recap. So let's move to the beginning. So that is suffix tree nodes, compressed and uncompressed. We have observed, we have understood that how all the things, how all the characters are added in suffix tree and compressed suffix tree. And the code we observed, actually we kept the code remaining. So this is actually tough. We'll be observing in the next video sections. And so that was suffix tree, and the time complexity I told you, that this when we insert in this manner entirely using the representation normal represent, it takes a very huge time big of n square, because here we don't compress, we just insert all the strings, long strings entirely, the entire strings is added. That's why it takes so much time. But when we come to Ukkonen's algorithm, it uses the common prefixes are used here. Common prefixes are used here, and the uses of common prefixes that reduces the time complexity from big of n square to big O of n. It reduces to big O of n, and that's why we utilize the Ukkonen's algorithm. So there are more few string algorithm, 4 or 5. I'll be uploading those string algorithms, and then we'll be looking towards the dynamic programming, that is the easy section, and strings algorithm and bit complex. So thanks for attending this session. Thank you. That's all. We'll be meeting in the next video.